Hi everybody, welcome to Module 2, where we're going to continue our work with geometric transformations. Last week, our geometric transformations started with a few key ideas. We learned about translations, reflections, and rotations. What's important to remember about these three transformations is that after any one of these three, or a combination of any of them, occurs, that you're going to be left with what we call congruent figures. And of course, congruency or congruent figures, which uses a symbol like this here, means that we're going to have figures that are still the same shape and the exact same size. This week, however, we're going to talk about a new kind of transformation called a dilation. And while congruency will still be discussed, typically when a dilation occurs, we get something known as a similar figure, or meaning that they'll have similarity. Let's get started. The first thing we'll focus on here is what a dilation actually means. And a dilation is simply a type of transformation that changes the size of a figure, but definitely not the shape. If it started as a right triangle, it will still end up as a right triangle, but the image or the second figure after the transformation could be either larger or smaller. Here we have an example of a dilation. We have triangle HJK right here that has been shrunk to form triangle H prime, J prime, K prime. Keep in mind that we use those apostrophes as an abbreviation for the word prime, and those prime symbols, or those apostrophes, that indicates what we call the image or the second figure after the transformation has occurred. Now, when you're examining or perhaps trying to evaluate dilations, we use something called a scale factor. Factor gives us a tip as to what kinds of operations might be helpful here, and we'll see a little bit of that here in a moment. In example 1 here, we see that figure R is a quadrilateral, obviously a rectangle, with the side lengths shown. We have side lengths of 5 units and 3 units. So they ask us if we take quadrilateral R and dilate it, or in other words, perform a dilation using a scale factor of 4, what would happen to that image and what would those new side lengths look like? And as you may have already guessed, since we are using a scale factor, factor is a word in mathematics that typically refers to the operation of multiplication. So if they're asking us to use a scale factor of 4, they are simply asking us to apply a factor of 4 by multiplying to each of those side lengths. So if we were to do that here, we would take each of the side lengths, 5 units, 3, 5, and then 3 units again, and multiply their lengths by 4. That means you'd get a new rectangle, or what we would call R prime in this situation, with side lengths of 20 units and 12 units respectively. We can also do the same thing with a figure that's found on a coordinate plane, although the process is slightly different. So here we have triangle FLA shown on the coordinate plane, and they want us to find the coordinates of F prime, L prime, A prime, if the preimage, meaning the original triangle, is transformed by a scale factor of 2. So this time, instead of multiplying by a factor of 4, we'll use a factor of 2. Of course, in our earlier example, we actually had the side length of our figure. This time, we could count those side lengths, at least most of them. But since it's on a coordinate plane, we're going to use a slightly different approach when applying this scale factor. The first thing that we'll want to do is actually find the coordinates of each one of the vertices, F, L, and A. Here you can see they've already found them for us, which is very helpful. After we have those coordinates listed out, we are going to use the same or a similar process as what we did with our original figure, which was a rectangle. We're going to apply our scale factor by multiplication. So here we've got vertex F, which is at -3, -2. We have vertex L at -3, -1, and vertex A at -2, -2. Once they're listed out, we can see here that actually all we're going to do is take each one of those values, the x and the y, and apply the scale factor one at a time. Once we do that, you'll see that we get new coordinates or ordered pairs over here on the right, which gives us f prime, l prime, and a prime. Now, the reason that we have to be careful with actually applying the scale factor and not just trying to multiply side lengths by the scale factor each time is because it'll appear that not only is the figure going to either shrink or get smaller or perhaps expand or get larger, is that its position could also change slightly as well. Here's what I mean. Once we plot the points for f prime, l prime, a prime, you'll see that the original triangle, FLA here, is a little bit more, we'll say, above and to the right of the image of f prime, l prime, a prime. Now, the image or the new triangle certainly is larger. It has been dilated, but notice again that it's in a different position on the graph, and that is a result of that dilation. The next thing that you'll explore doing is how to actually find the scale factor. So instead of being given the scale factor and trying to dilate an image, you might find yourself having to actually find that scale factor once you have both the pre-image and the image themselves. That would look something like this. So here we have triangle R, which is created using a dilation. I'm sorry, we have triangle R prime created using a dilation of triangle R. So we're going to try and find this scale factor. So they set it up here for us, but I'm going to try and give us some different language to use as well. So it does say in order to find the scale factor, we're going to choose two sides that are corresponding, meaning in the same position on the triangle. So here you might consider using the quote bottom sides of each of these, or the longest side on each of these would work well, as long as they are again corresponding. So we're going to set up a ratio, which of course in most situations looks like a fraction. But here it says with the image measurement on top and the pre-image measurement in the denominator. So we're going to write that down, and I'm also going to give you some more layman's terms to use that might make this a little bit more approachable. So here's the style of the ratio they would like for you to use, image on top and the pre-image information in the denominator. But just again, to give you some more common terms here, when we say the image, keep in mind that that's the new figure, the one that has been translated, transformed, whether it was translated, reflected, rotated, or now dilated. That second version is the new one. So they want you to put that information in the numerator, and the original figure, the original triangle in this case, that information should go in the denominator. And this might help you make a little bit more sense of what they mean by image and pre-image. And I wanted you to have access, or I wanted you to have access to that type of thinking before we continue. Of course, you can see here on the left that they've put that together for us. They went ahead and took the information from the new triangle, or the prime version, which was a side length of 5 units, and they used the information from the original, or the pre-image, which was a side length of 10 units, and wrote that ratio comparing the two. Of course, you'd want to simplify if possible, and many times it is, and get a scale factor this time of 1/2. So what you'll notice at this point, whether you're finding scale factor or applying scale factor, is that scale factor can use all different types of numbers, but the reference point for scale factor is actually going to be the number 1. And what I mean is this, if the scale factor is the value 1, then we know multiplying by 1 actually doesn't change the value of a number or a coordinate or whatever else the application would be here. That's because multiplying by 1 is the identity property, meaning, again, it doesn't change the value. So if you have a number that is less than 1, as a scale factor, you should identify that then my image, or the new figure, is going to shrink, or in other words, get smaller. However, if you happen to have a scale factor that is greater than 1, of course that means your image, or your new figure, is going to get larger. So keep that in mind as we continue to work here, because that's a key piece of information that can help you make sense of a wide variety of different situations that you will see. Here's another example of a time when you're going to be asked to find the scale factor. But the concern we have here is that you're not always able to either measure or count the side lengths of a given figure. That ends up being the case here is if, for example, we were trying to find the side length of side BA, we wouldn't actually be able to do that without some more advanced skills. The reason is that side uh, BA or AB, however you'd like to list that, doesn't actually follow the grid lines that are on our coordinate plane here. So that side length isn't actually exactly 1 unit, it's actually a little bit more. So what do we do when we can't actually count those side lengths? Well, what you're going to do is actually very similar to what we did on an earlier example. When we don't have necessarily the side length information of our figures, we're going to resort to using the coordinates or ordered pairs for a variety of our vertices. Now, the good news is we can use any of the vertices, and it can be helpful to explore more than one corresponding corner. I'm going to go ahead and just use corner A this time. Um, Although you can feel free to try this with B or C to test your own understanding. So if we were to go ahead and list our coordinates for A and of course then A prime, we would find that vertex A is actually at 2, 1, whereas A prime is going to be at 6, 3. Once we have this information, then we have enough to help us again explore the scale factor. Now, yes, the scale factor does help describe how the side lengths are changing, again, getting larger or smaller, but the coordinates also lead us to some of that same information. The first thing that I'd ask you to think about is whether our image, meaning the new figure or the second one, has it increased in size or has it decreased in size? In other words, as we go from ABC to A prime, B prime, C prime, did the triangle get larger or smaller? And it very obviously got larger. But what that tells me is that my scale factor should be a number greater than 1. If that didn't happen when I go to complete the calculations, I know that I may have done something incorrectly. Now, I also remember from just a little bit ago that I know I'm supposed to be taking the new information. In this case, that's something from my new coordinates, and I'm supposed to write that as a ratio over the original information or the pre-image, and again, coming from my coordinates. What's cool here is that you can actually choose either the x values or the y values, but you do need to choose one of them. And again, testing both wouldn't be a bad idea. Once you have that, you're going to go ahead and complete your ratio. I'm going to use my x values, so I am going to use the new x value, or what I'll call x prime, over the original x value. Now, x prime, of course, is a value of 6, whereas x from the original triangle is 2, and we can then simplify this ratio to find our scale factor. And of course, 6 over 2 can be simplified and just gives us a whole number of 3, meaning the scale factor for this situation would be 3. Now that we understand a little bit more about dilations, we're going to go back to the larger category that they belong to, which of course is similar figures, which we mentioned at the beginning of the video. Similar figures, of course, indicates that the shapes or figures will have the same shape and angle measures, but different sizes potentially. Just as an added note, similar figures or similarity is described using this little tilde or this little curved line that we have here. You might remember from last week that when we talk about congruency, which means same shape and same size, we use an equal sign with that same little tilde or curled line above it. When we talk about similar figures, we're removing that equals sign, which will probably come apparent as to why in just a little bit. So let's talk a little bit about similarities and differences between these two ideas, being whether figures are similar or whether they're congruent. So if two figures are similar, they have the same angle measurements. That's also true if two figures are congruent. If we have similar figures, their side lengths, they can be the same, or they can actually be different. If they're congruent, though, they do have to be the exact same size. Now, when we talk about transformations, the transformations that could result in similar figures, well, those could be translations, reflections, rotations, or even dilations, it could be any one of those that would result in similar figures. However, congruent figures only occurs from the first three: translations, rotations, and reflections. Dilations will not result in congruent figures, and that's that primary difference between the transformations we did last week and the ones we're doing here now. So let's not overcomplicate this. When we talk about similarity or congruency, well, we're asking you that one idea. Can the figures be the exact same size or not? So for example, in practice problem 1 here, it says, are the figures shown similar or congruent? Do they have those properties? And the general question should simply be this: are the two figures the same size or not? Of course, they're not the same size, so we would say that these two figures are similar, not congruent. The last thing we'll be talking about are scale drawings. Scale drawings are very popular to use when perhaps drawing blueprints of houses like you see here, or in other words, drawing very large things on much smaller pieces of paper, or even taking very, very small things like diagrams of computer chips and trying to enlarge them to make them easier to see as well. And there are a wide variety of things we can do using scale drawings, but what's important to know moving forward is that scale drawings are basically a application of the scale factors we talked about just a little bit earlier. Of course, here with these scale factors, we tend to have different units like inches and feet, for example, here. So we'll take a look at this problem and make one main point before we wrap things up. It does say to take a look at the scale drawing of JJ's new room, which we see here on the right-hand side. It says in the picture, a half inch on the drawing actually translates to 1.5 feet or 1.5 feet in real life. So in other words, every time a half inch of something is drawn, it's actually 1.5 feet in real life or in the real room. So they're asking us to use that scale drawing here to calculate the actual dimensions. In other words, how big is JJ's actual room, keeping in mind that here it just says that the drawing is 4 inches by 6 inches. So they give us information about the actual item, and of course then they ask us to compare it to the drawing itself. And while technically we could start to process through this problem and find the size of JJ's actual room, finding a unit rate in a lot of these scenarios can be very, very beneficial and help us avoid errors. Of course, if we find a unit rate, we're really just trying to say, how much does 1 inch represent in the drawing as opposed to a half of an inch or whatever other value they give us. And down here, they do remind us that unit rates can be found by dividing. So we're going to take the information from the actual room, and then we're simply going to divide it by the information we have from our drawing. And that's what you see here. The actual room had a dimension of 1.5 feet, according to what they told us. And the drawing said that a half of an inch represents that amount. If we go ahead and divide those key pieces of information, we would take 1.5 divided by 0.5. Of course, 0.5 being the same thing as 1/2, which would give us this information here. 1.5 divided by 0.5 is 3, which really means that 3 feet is represented by 1 inch in the picture. And that can help us then find further information because using a unit rate, again with a denominator of 1, that gives us some very approachable information. And those are all the main ideas for the new information that you guys will be working on this week. This will also finish up our work with transformations. Again, last week we looked at congruent figures, which revolves around translations, reflections, and rotations. And this week we transferred over to similar figures, which is a result of dilations. Good luck with this new information. We will see you in class to practice some more, and let me know if you guys need any help. Good luck.